My name is Dr. Farhan Riaz, and this is the computer vision course that I'm teaching at the National University of Sciences and Technology. I'm using the slides that have been prepared by Professor James Hayes as part of computer vision course that is being offered at Georgia Tech University. Now, the important question is how can we emulate the presence of corners in an image? How can we detect that? So let us consider the small mathematical equation where we are trying to calculate E of uv. W is a window. This window is represented by this red block. I of xy is the image intensity, and I of x plus u and y plus u is basically the shifted image intensity. So what we are saying is that if we are shifting an image by a factor of uv, u across the horizontal direction and v across the vertical direction, then how do the intensity changes take place in the image? So effectively, we are looking at a very high value of E of uv to find corners. Um, because if the value of E of uv is very large, this means that there is a strong gradient that is present in the image because this magnitude is very large. If this magnitude is very large, of course, this energy is going to be high. So this is the kind of a region that we are looking for when we are trying to detect the corners. We can see over here that at 0 0, which means that when we are not inducing any shifts in the images, this value is going to be E of 0 0, and it will be dark because we are basically taking the difference of an image within this window with itself, which obviously is going to be 0. And if you can see, as we displace the window upwards, this energy is large over here. And if we displace this window in this region, as the vertical displacement causes a very large value of this energy. So this is why we have bright region over here, and this region is dark over here because we are basically calculating the change in intensity by inducing zero shift, which obviously is going to be 0. Now, as far as this window is concerned, we can consider any type of window, or we can define a window function. For example, we can have this window function, which is a step function, and then this window, which is basically a Gaussian function. This Gaussian function is quite significant because we know that the neighboring image pixels are highly correlated, and as you know, we are talking about pixels which are far away from one particular location. The dependence or correlation between the pixels will significantly reduce. So it is a reasonable assumption to consider this window as a Gaussian function, which means that it would not be just a window in which we are placing all ones, but it actually is a Gaussian window where the significance of a pixel is actually reducing as we go from the center location. And basically now our objective function is to find how this function E of uv behaves when small shifts are applied in the images. And although this equation appears quite simple as far as the understanding is concerned, it's very important to see what is the computational complexity if we are trying to employ this equation. And what is the order of complexity? So just to give you an idea, the order of complexity depends upon three important variables. One important variable is the width of the window, the width and height of the window, of course, and then the shift range, the u and v parameters. These are important parameters, and then what is the resolution of the image. So according to a rough estimation, if our window is of size 11 by 11, and if the shifts that we are applying, they are also corresponding to 11 by 11 shifts. And if the image resolution is 600 by 600, then roughly we have to perform 5.2 billion calculations if we want to just calculate this energy in order to find the corners. And this number actually corresponds to 14.6 thousand calculations per pixel that we need to perform once we want to calculate the corners in the images. So this is a big number, and obviously it is not practical to perform corner detection using precisely this equation. So in order to do this, there are several things that we can do. First of all, let us find out how this function actually behaves for small shifts. And in order to do this, we will recall the Taylor series expansion of a function n of a function f that can be approximated around the point a as this particular equation. As an example, we can find the Taylor series expansion for a function e raised to the power x as follows using the Taylor series. And over here, a is equal to 0. Well, a reasonable approximation of the function e of uv can be actually found by the second order Taylor expansion that can be written as follows over here. And well, we need to keep in mind that e of uv is a two-dimensional function in contrast to the function that we have seen in the previous figure. So let me just try to compare these two equations. So this is f of 0. Then we see that there is the first derivative of this function, and then x minus a, and this is represented by this particular equation where e of u is the first derivative and e of v is both of these can form actually the first derivative. Since we have a two-dimensional function, therefore the first derivative will obviously incorporate the derivative in both the directions multiplied by u and v. And over here then we have the second derivative and multiplied by x minus a square. So in order to satisfy this condition, and there is also a 1 by 2 over here, so 1 by 2 is taken as it is. This u into v and u into v for the second term in the previous equation, and then we have the second order derivative that is represented by this matrix, which is e of u 0 0, which is the evaluation of the second derivative of e with respect to u at location 0 0, and so on. This is how all these terms they are defined. And obviously we are saying that this is an approximation because we are basically neglecting the rest of the terms, assuming that we are just trying to generate an estimate of the Taylor series expansion.